Okay. I mean, geometry's, well, one of the many passions in maths education that I have. It was a research area for me in Australia. And as part of my role over there, I did a lot of working in classrooms and seeing what it looks like in Melbourne classrooms, which was really interesting. So what you're seeing here is a picture of some students. They are year 3 in Australian terms, so they're year 4 in ours, so the years are slightly different, but we'll see more of what they're trying to do as we go along, because I'm going to try and show you some snapshots of classroom practice and see what that actually looks like. I was always inspired by geometry by a dear colleague of mine, Barry Brocas, when I worked at Palmerston Teachers College, and I have vivid memories of polyhedra hanging from the ceiling. And anybody who's listening who went to Palmerston Teachers College during Barry's time there, you would remember him fondly, and his passion for geometry, and how his feeling that it was often the left out part of the New Zealand curriculum. What does the current 2007, I'll show you what the revised one looks like as well, curriculum actually say? And we pleasantly describe the curriculum we wrote in 2007 as the back of the postage stamp curriculum, because we were very constrained about the space we had to write achievement objectives. And I know that the writers of the revised one feel the same way, but they've got a lot more space than we had. So this is what the achievement objectives say. And of course, you have to do quite a bit of interpretation. So when level 2 says identify and describe the plane shapes and found in objects, think of that as something like in 3-dimensional space, I can recognize a triangle in a 3-dimensional object. So it might be a pyramid, for example, or I can see it on the face of a building. And I can describe those plane shapes that I see in 3-dimensional objects. You start to move into a different level of sophistication at level 3, where you're actually trying to represent 3-dimensional objects with drawings. And of course, drawings are flat, so you lose information as you represent something that has depth in a flat space. Models, of course, is the likes of constructing solids and maybe cube buildings as well, things like that. I like to emulate what happens in Singapore, where they make very firm connects between the properties of 3-dimensional objects and some of the measurement concepts we might want. And what I like to try and do is kind of connect 3-dimensional objects with the idea of volume, for example, 2-dimensional shapes with the idea of area. So I think they go hand in hand, and there's a lot of potential for connection there that we don't exploit as much as we should. In fact, in Singapore, a lot of the algebra that they do at we would call year 7 and 8 actually falls out of the measurement that they do. I'm just having to move everyone's face, sorry, not literally. So when we get to level 4, we can see this word classes, which is a really interesting idea. So a class is, if you like, a category of solids, we'll say in this case, that are defined by the properties that they have. And we'll bring that word properties to life a little bit more for you, because the words features and properties are also used in the revised curriculum. They're used as if you understand them, and we'll try and make that clearer. There is a difference between a feature and a property. We also have this whole idea of relating to 3-dimensional objects to the representations that are 2-dimensional. So there's that going on all the time, and you'll see that in the flavor of what we do. So here again, I'm saying, well, let's use the opportunity when we're dealing with 3-dimensional objects to bring in some of those measurement concepts as well. Now, if you look at the outcomes, says he optimistically, looking at the outcomes. Something is, oh, here we go. It's just frozen a little bit. So these are just the outcomes from the revised curriculum as it stands at the moment. And you'll see very similar sorts of things, well, possibly a little bit more clarity because there's a little bit more space, but the same kind of thing. So whatever we show you today is not going to change very much no matter what happens with the curriculum. So some of these things like drawing nets and what have you will come to life for you, I hope. Okay. So let's kind of think about the idea of, I've got so many windows going on here. Here we go. Okay. So a feature, as it's described in the literature, is a kind of characteristic. So usually they're perceptual characteristics. Little kids will tell you, and they did it on Thursday, this is a round shape. It's or this one's pointy. It's it's got a sharp bit. They'll notice those kind of things. They're features, right? So they're perceptual characteristics of a shape. This thing really is. So this is pretty typical, and they were 5-year-olds in the new entrant class at the school I was visiting. And they had lots of words to describe these three-dimensional solids they were messing around with. Sometimes the features can get closer and closer to properties because they start noticing things that are geometric in those shapes. So when they say, oh, they're all the same because they have squares in them, then they're actually getting closer and closer to the idea of a property. But let's just say a feature is something that you observe, okay, or you feel. Now, properties are different because they involve a mental process where you connect features. So some of those properties aren't used to define the class of shapes, but they're interesting ones to have anyway. For instance, a student might say to you that and they might signal with their gestures of their hands and say, well, the faces of the cubes, they mightn't have the word parallel. Hope they do, but maybe they don't. They say the faces are parallel. And they can sometimes notice that around each corner there are 3 squares. So they can be properties of a solid, but they're not the ones we use to define that class of solids. So a defining property is one where it actually is it's the means by which you decide whether a solid belongs in that class or not. And it's kind of interesting to think about all the things you know about a cube, and the definition comes as simply as it's a 3D shape bounded by 6 squares. And all the others kind of fall out of that definition. So let's go back. A feature is something you perceive, you can feel, see, and a feature is when you engage in the cognitive task of connecting those features. Because the shape doesn't do it for you, you have to do it for yourself. That's what makes it a property. Okay, what are the common 3-dimensional shapes we would work with in primary school? Well, here are a few of them that I'm hoping that most students would be familiar with. They may not necessarily know the names for them. Why is naming a solid important? Because it gives you a language to talk about it. It's, if I'm trying to talk about the sphere and I don't have that word, then I'm kind of making likeness to real life, and I want to move beyond that. I want to be talking about that shape called a sphere. They're not necessarily balls. They can be lots of things. The Earth is close to being a sphere. So the language is important. It gives us a label for something, and then we can start defining that something that we're talking about. And we're not, we can come to a common agreement about what that object is, called a sphere or a square-based pyramid or whatever we're talking about. So they become the main shapes that we would choose to classify. Now, let's think about some useful words to describe the parts of 3-dimensional shapes. So a face is a flat, it's a plane shape that makes up that solid. So it's always a polygon. Well, careful about that. You mightn't think that a circle is a kind of polygon, but let's just say that it's a flat space that makes up that solid. Corner and vertex are the same thing, really. The more general word is vertex, but corners can be used interchangeably with vertex. And an edge is like the edge of a table. It's where two faces meet. So they're useful words because they become the means by which we actually classify and find relationships among the solids that we're working with. Then we have things that sometimes have flat shapes, and sometimes they have curvy bits. And the name given to something that bends, doesn't stay flat, is a surface. And now I can't see what behind. Here we go. So I just find it really nice to use the words like parallel when we're saying, say you take a triangular prism like this and say that the end faces are parallel to one another. And as I say, gestures are really nice for that, using your hands to say show what you mean by parallel. And faces that are opposite are on the other, if you like, on the other side of the solid to the one you're talking about. So in this case, the triangular faces are opposite. And we can also have a word for next to. So the rectangle and rectangular faces joining the triangular face, so it's adjacent. And those words become very, very important later on, certainly at secondary school, when you start exploring things like trigonometry. Kids actually having those words in their vocabulary, that's a very useful thing to have happen. And it's one of the areas that lets us down in the likes of TIMS, because our kids don't have words like perpendicular anymore. We don't seem to teach that. Maybe we should. And it gets in the road of them being able to answer quite relatively simple questions in TIMS. Okay, I'm not going to dwell on the detail because it gets extremely boring if we do, but what I will kind of exemplify this detail as I go along. So whereas the achievement objective is quite broad, and we'll make these slides available to you, what I've done there is just flesh out the kinds of things that I would want students to be able to do at level 2 under that achievement objective. And I've done the same thing here at level 3 and level 4. So it's giving you more, if you like, finer grain size about what we're expecting to have happen. And the other thing I think, even with achievement objectives, there's a tendency to look at the curriculum and say, oh, okay, they don't start representing objects with drawings until it's level 3, so we'll leave that to year 5 and 6. Believe me, young students can represent solid objects with drawings. So you could be leading up to that quite a lot, right back as far as when they first start school. And you'll see that. We'll show you an example. So I'll just leave that without spending ages and ages, and I'll just accept that I'm going to show you examples that do those things. Okay. So when we're talking about classifying, there used to be when I started teaching my little 5-year-olds, my first year teaching, classifying was a big deal. And by that we're talking about grouping shapes, 3D shapes, solids, by their features or properties. So we can get more and more sophisticated at how we do that. And it should start right way back when they're 5. So it might initially be as simple as you're either in one group or in the other. So if you take 3-dimensional shapes, your little 5-year-olds are pretty good at telling you the ones that are round from the ones that are sharp and have corners. They can get as sophisticated as saying these ones have got rectangles, these haven't got rectangles. So that's what we would call a binary sort. So you're either one thing or the other. Of course, life's never quite that simple. So you might then be trying to sort out, as you see in the picture, a classification system where you have two things going on, two characteristics, features. They roll or they don't roll. And you might combine that with color and size, for example. So your sophistication and classification grows from being just using belong or not belong to actually considering two things at the same time. Back in those days, back in the dim dark days of my 5-year-olds, we used things like talked about intersections, and you could have the circle road and you could have the yellow road, and could you find the blocks that belong in the intersection? And my 5-year-olds were very proficient at dealing with two attributes at the same time, color and shape. We used to use a road sort of diagram to do that. So when you are moving beyond that initial sorting, you are starting to move towards definition. So by definition, you mean the characteristics, properties of that solid that allow you to decide whether an object belongs in it or not. So so we might be trying, for example, to look at cylinders, some examples of cylinders, and say, well, what's the same about all of them? And we might come up with our own kind of working definition of that they've got two circular faces and a surface that wraps around. The really important difference between your sorting at levels 1 through 3 and what you're starting to get into level 4 is when you're defining a class of shapes, you're not talking about particular individual shapes. You're talking about the shapes that could belong in there, hypothetically, right? So that sounds like a subtle difference, but it's not. So you are coming up with a definition, and then you can characterize the shapes that belong in there. Part of that whole deal is what does belong and what doesn't. Is this an example of a prism, for example, or isn't it? And if it isn't, why isn't it? And sometimes you can get situations, again, back in the dim dark days, we used to do lots of this sort of thing with our phys hoops. You probably still got those, the hula hoops. And deciding, so if I've got a classification system there, is it possible to have something that belongs in both places? And so these little folks here, you can debate some of this if you want to, but does it have a curved surface, it says on the left-hand hoop? And is it a prism? And it's really interesting to see that these students, they look like they're, not very old. They look like they're about 8 years old, and they have decided that a cylinder belongs in the intersection of those two classes, right? So the class of shapes that have curved surfaces intersects with the class of shapes that are prisms. So we need to do lots of stuff around classification, not just for geometry. It's very, very important for our statistical work as well. Okay, so we're going to have a look. I'm going to try this, and we're going to see what happens. It's been playing up the little projector here because it's wanting to take over the camera. So we're going to just see what happens when we do that. It'll either be carnage and chaos, or it'll all work swimmingly. So hopefully you can see something that looks like a whole collection of shapes, and it looks pretty complicated at the moment. What does that set look like? I use these a lot. I'm not advertising them. I'm not trying to sell them to you. I'm just saying that I find them really handy for lots of things, and they're really useful for measurement because, as you can see, they've got a nice little hole in them. You can fill them up with water. So we've got a collection of shapes there, and we're going to try and do a little bit of on-the-spot classifying here and see if we can see things that are the same in some kind of way. That's how I would start with students. Can you see any things that are the same? Well, they might do what the little kids have done and say, okay, I think that they kind of all belong together. I hope that sphere doesn't go rolling off the table, because they've got curved surfaces. Great. Okay. That's one way we could classify them. Often kids will tell you things like this. They think that these ones belong together. Okay, well, why do they belong together? And they'll try and tell you about the apex here. It's nice to give them that word apex, that they are solids that have a pointy top, if you like, and they all have a base. Um, and of course, we know them as the set of pyramids, so you can kind of start saying, okay, we might describe this as a triangular-based pyramid. Wonder why we do that. Well, the bottom of it's a triangle. What would this be called? Square-based pyramid. Does that make that a circular-based pyramid? Interesting, isn't it? So it's quite nice when you start exploring this idea of, okay, what would come next? It would be a pentagonal-based pyramid. It would have the base would have to have 5 sides. Then we'd have a hexagonal-based pyramid. And you can kind of, it's really handy from a measurement point of view to be able to view a cone as a kind of pyramid. Most definitions will have it as a curved surface, naturally enough, but from a measurement point of view, it shares the same volume formula as these ones do. So that's a handy kind of thing. And kids seem to be quite comfortable with that idea that if you just kept on going forever, my little 5-year-olds used to tell me that if you keep on going, you're going to end up with a circle. You go, oh, okay, it's interesting. So what we're really starting to do now is we're really starting to define a class of solids that these belong to that same class because they have these properties. They have a top vertex corner, they have a base that names them, and they also tend to notice that they have triangular faces as well that converge on that vertex. So that's nice. That's one class that seems to fall out quite easily for kids. This class is sort of interesting and one they should be familiar with. I think I should include this guy in there. That can be called a cuboid. Funny, it doesn't look much like a cube, but it's a rectangular prism. And what's the common characteristic of these solids? Come back, cylinder. Well, they have opposite faces that are the same, that are parallel. What else do they have? Well, those opposite faces are connected by rectangles. So if I look at the triangular prism, it's these faces connect the end ones. The definition of a prism is that it has constant cross-section. Now, that sounds a bit highfalutin, but if I think about this triangular prism as being a loaf of bread and I sliced the loaf of bread like that, the cross sections I'd get would be constant. They'd be the same as the base and the top. They'd be triangles. And if I cut the pentagonal prism parallel like that, I'd get the same thing. Again, is a cylinder a kind of prism? Well, it has lots of the characteristics of a prism, and from a measurement point of view, it's really useful to think of it belonging to the class of prisms, even though most definitions will have it as a closed surface. So that kind of that approach to classification, where you get a group of solids and you say to kids, well, which one should we put together and why will we put them together? That generally leads to them noticing properties and you coming up with some definitions of this particular class of solids. You can do that with 2-dimensional shapes, of course, and I'm not actually convinced that it's easier to classify 2-dimensional shapes than it is 3-dimensional. They can get very sophisticated as well. So I will come back to that in a minute. Now, hopefully it hasn't lost me and I can go straight to here and see what happens. There we go. This looks promising. Hopefully you are seeing the PowerPoint again. So let's see if it's going to move. Go, go, go. Sometimes it takes a while to catch up with itself. There we go. Okay. So let's talk about common representation of 3-dimensional shapes. Anybody who's doing some university study about representation, write this down. Write this guy's name down. He is French and has done some brilliant work about different forms of representation and connections between them. I'm not going to get into his research work. I'm just going to suggest to you that if you're interested, he's interesting to read. What are we expecting? What are some of the representations we're expecting? Well, we're expecting kids to be able to handle the idea of viewpoints. Now, those viewpoints in this case, on the left-hand side, are, they can be a model made with cubes, and we're looking at the top, the front, the right-hand side. They can be looking at a landmark from the north, from the west, from the bird's eye view in the same kind of way. This is a bit more sophisticated, I think, when we start trying to draw some of these solid objects on isometric paper. It's a kind of perspective drawing, but not truly perspective. We don't have a vanishing point. It just helps us to keep all the edge lengths the same. So that we would expect kids to be proficient and experienced at coming across these kind of representations. We would expect them to know something about nets. Let's just say that giving students a pre-created net for a cube is not going to help them geometrically at all. Certainly not going to help them visualize anything. So we want students to be able to construct their own nets for the solids that they see, and we'll show you that they can do that. And that can get really sophisticated. So there's a whole lot of research stuff around what they call surface development type tasks like nets. One that you don't see in our curriculum, and I wish it was there, because it's very important to lots of STEM fields, is the idea of being able to visualize a cross section. When you cut something, and you think about the shape that you form when you cut. And lots of STEM related professions and art fields rely on people being able to do this. And I'm pretty sure the builders who are working on my house at the moment, they know quite a bit about cross sections of things. You just see them doing things naturally. Okay, so they're the main things we're looking at in terms of representation. You always win people over these days, I'm told, if you cite neuroscience. I'm a bit skeptical sometimes, but what we do know is that vision of all the senses we use is natural. I know people say they're a visual learner. Everyone's a visual learner, because over half of our brain's resources are devoted to visual processing. I imagine that changes if you lose your sight, but for most of us, that's how it is. And we learn best through some sort of visual medium, especially when it starts being connected to other semiotic forms like language and science, the words we use and the ways we represent ideas. So if we just rely on speaking and words without a visual image, we get what we deserve. Now, people have tried to classify how people think about three-dimensional shapes, or shapes in total. And this is one way. Kosnikov and her colleagues, they kind of characterized sort of what they're not really polar opposites, but the kids that can draw the phone book, they can. I can remember a little guy I had when he was in year 5, and he was the most amazing artist. Like, they're the kind of people that can kind of capture a static image and they can just draw it, and you say, wow, that's just amazing. And Kosnikov and colleagues characterize the difference between people that are strongly, if you like, they capture as it is kind of images, and very strongly, and can recreate them, from the kids that tend to be better at things like mental rotation tasks. They're the students that look at a three-dimensional object and think about its characteristics and its properties, and they try and use those properties strongly to imagine what happens as they're turned or they move relative to the object. Now, it turns out, of course, that life is never that simple, and you might think yourself sometimes that you can operate quite comfortably on either side of the other. So creating kind of false binaries like that is never particularly helpful. But what it does do is show you that there's a way of kind of if you're reliant entirely on just trying to be able to visually process something, rather than thinking about the properties of the object that you're transforming or working with, um, then you're going to be quite limited. And it's the interaction between them that really matters. And I'm going to show you, this is Charlotte. She's, hopefully this is going to play, and hopefully I've got the volume up and everything. And what Charlotte is one of the students, she's year 6, think year 7 New Zealand terms. She's at the end of primary school in Victoria. And she's trying to visualize whether this net that you see will fold up to make a cube. Now, I'd like you, before I play Charlotte, I'd like you to think about yourself about whether that net would fold up to make a cube. So just give yourself a few minutes, short time to do that. So now we're going to have a look and see, hopefully we're going to have a look and see. Hopefully you can hear. But oh, sorry, I had to stop. I just submitted somebody, and that's a mistake.
Sorry to interrupt, Vince. Are we supposed to hear something?
You should. I'm hearing it, but you're not. Okay, well, that's helpful.
Yeah, we
Okay,
can't hear.
all right. So I'll just stop it. Okay, I don't know why that's not working. Um, so essentially, what you can see kind of the gestures are telling you everything, even though you can't hear. So she's initially saying, "No, it won't work," because that can't go anywhere. F can't go anywhere, and then she works out, "Oh, hang on, yes, it can, because if C folds up, F will wrap round. Yeah, it will work." And then I say, "Well, what about A and B? What's going to happen to them?" And she goes, "Oh, no, it doesn't work." And she wants to move A somewhere else. And I say, "Well, leave it as it is. Does it work as it is?" Um, the point is that she goes through about 4 iterations of, yes, it will work, no, it won't. And what's actually happening and I actually, hang on, we'll go past it. If you analyze what's going on, she's kind of visualizing the action of folding. And she's connecting that visualization of acting with what she knows about the cube. So when she's kind of saying this one, and you can follow the dialogue, this is a diagram of what she says will actually happen. It looks complicated, but it's not. What are the actions that she'll perform? But there's this continual dynamic interplay between what she sees and imagines as it folds and what she knows about the shapes. And in particular, the notion of faces being at right angles, faces being parallel, really, really important. So in short, what's really important are both of those things and the interplay between them. Yeah. So it's not just about imagining an action of folding up. It becomes really powerful when you connect it to what the properties of that particular target shape are. So I'm sorry you couldn't hear it, because she's quite delightful. But anyway, so let's show you some real life stuff. This is a colleague of mine from Melbourne. She's retired now, but wonderful practitioner. Learnt lots from Andrea. And these are little tackers. So they're 5-year-olds. And what do they call them? Foundation is the proper title. But they have another term for little guys in Melbourne. Okay, so this is how she starts. She basically starts by showing them, well, I wonder how if I made this, I wonder how I would draw it so somebody else could make it. And the kids go off and they have a go at trying to think about what it looks like when they get down at eye level and the top and all that sort of thing. They have big discussions about what's the best way to show this. They're only 5. And then they start trying to draw the thing that they've made. And Andrea hasn't said, oh, draw it from the top, draw it from the front, draw it from the side. She simply said, oh, I wonder what it looks like down here, looks like from here. And they have tried to replicate. So we have some interesting spellings of sideways and stuff. But down means, this is my kind of top view. Now you might notice, well, it's probably clearer in this picture that they have a lot of trouble not showing what they don't see. That's the double negative, I know. But there's a tendency, you see this little guy here, you look at the bottom left, he's trying to tell you that there are 2 cubes stacked on top of one another. So he wants to tell you some information about the things that he can't actually see when he draws like this. And that's a common issue with kids. We've found using a digital camera and going around actually taking a photo of what they've made and then showing them is really helpful. It was the other day we were doing the same kind of thing with older kids, and when they saw the picture the digital camera showed, they were much more comfortable about not drawing what they didn't see. So the message here is, don't start by introducing necessarily the formal way that you might represent a three-dimensional object. Let them explore how they're going to draw it themselves. I've got some very clever year 8, they are all boys actually, not and one of the things they have really struggled with is I will give them a three-dimensional solid and then I'll say, well, have a look at this from the top. Now go to the whiteboard and try and draw it. And they're finding that really challenging. So the idea is let them explore themselves the way that they might represent it. And that will actually lead you to the more formal, plans view that we're used to using. If you're interested in any of that, there's a term called semiotic chaining, which means start with their natural ways of representing and then move to more formal ways later on. This is me with, I think these students were year 3 in Australian terms, year 4, and we looked at packets and thought, what could you tell me about the shape of these packets from what they hold, which is more enticing. And the first thing I wanted them to do, we just started with the cuboid packet. And I said, well, just turn over the piece of paper and sketch what you think it would look like when I open it up. And so here's some examples. Now there's a lot right and some things wrong, right? So they've recognized the faces in this case. They're not quite sure how they align, and they're certainly not very clear about what measurements have to be the same. So that was pretty common. That was their sketch, attending to the faces. They seem to have that idea of the central rib, don't they, of 4 rectangles in a line. And then we kind of opened it up and we had a look and said, well, what has to be right for your drawing to be, really accurate? It would actually fold up and make what you're trying to. And some of the kids had an idea of matching edges, but a lot of them didn't. This kid's trying to explain that. And then on the other side of the paper was just 1 centimetre squared paper. And I said, well, okay, now you've got your big chance. See if you can make something that really works. It will fold up exactly to make the cuboid shaped box. And they did that. But we had a lot of this kind of thing with, do you see how Nathan's, when he folds it up, he's got one side, he's trying to form an edge there, and one side is longer than the other. That was very common. And we had lots of discussions with different kids about, well, what lengths need to be the same if this is going to work. And they basically spent quite a lot of time getting their net absolutely right. Sometimes by trial and error, more often than not, they were kind of thinking really hard about when you folded it up, what met what and why it had to be the same length. And there were kids who did this quite proficiently, and I just said, oh, well, here's the triangular prism. Have a shot at that and see how you get on, which is quite a big step up. It's quite a lot harder. Yeah, big discussions about how did what you make match what's here. And those little shapes down there are called polydrons. I've got some here. Doubtful whether I'm going to have time to show you all of those things, but they're very handy. I'll show you how handy they are. Share. Here we go. You can see that. So that was made by those year 8 boys I was talking about. We have way more sophisticated ones sitting in our office at the moment, where kids have put together from just the picture, had to actually put these things together. They're going to explore those. Here's another one, which might look more familiar to you. That's an
just get you to
icosahedron.
Lift it up a little
Lift
bit
it
higher.
up. Lift it up. Is that okay?
Too high.
That's better.
Down a bit. It's better.
There we go. Down a bit. Okay. We can do lots of things with these. What we've been doing with some of the students is actually exploring how do we actually go about counting the number of faces, edges, and corners on a solid. Now, it's nice and easy when you have something like this. Because it's very easy to go 1, 2, 3, 4, 5, 6, 7, 8 faces on this, an octahedron. But actually, and counting the corners is pretty easy too. A number of corners, I mean, and edges is similarly pretty straightforward. But when you get into solids like the icosahedron, which is made up of 20 triangles, I think, yes. Is it? Okay, I think it's 20 triangles. How do you actually count the number of edges? And they've started to have to reason their way through that and imagine all these 20 triangles all laid flat. There's 3 sides on every triangle. That means there's 60 sides and 60 corners on those triangles. We're using 2 each time, so how many of these edges should we have? Well, it's 60 divided by 2 is 30. There should be 30 edges. How many corners are we going to have? Well, there's 5 corners of triangles being used to make one of these vertices. So if I go 60 divided by 5, I get 12, which is the number of corners on this. So there's lots of sophisticated things you can do with polyhedra, and I'm very conscious that I'm probably running out of time, which is pretty normal. And we'll just show you one more thing because we could go on for a long time. I can now see my application. That's very good. Just okay. We owe it to students to encourage generalization. So generalization is something that works all the time. So if you take the little guys I'm working with there, the year 3s or 4s, we're probably not at a point where we can push the generalization too hard, except for maybe some students, but certainly students that are older. We might make several nets for prisms. We owe it to them to ask them what's the same about those and what's different. And do you see how important it is then to connect what you visualize with your definition of the properties of prisms? And students that do that very quickly say things like, well, they've got 2 faces the same. Well, what do you mean? Oh, well, let's look at this one. It's got 2 hexagons. Oh, does it? Okay, yeah. Does this have the same thing? Yes, it's got 2 squares. This one's got 2 triangles. Oh, what would an octagonal prism have? Oh, it would have 2 octagons. Do you know how many rectangles it needs? And they start saying, well, it needs the same number of rectangles as there are sides on the end faces. So what you're starting to do is to come up with a generalization that is true of all nets, whatever the prism is. Well, they're right angle prisms at the moment. So I would love to go on more, could do. and you are keen that we stop now because we're over time.